In this video, we'll take a look at DC offsets as they relate to Fourier series. So we have here a signal x of t, which is periodic with a period of 3 seconds. You can see it repeats itself every 3 seconds, and it takes on 3 different values. Between t equals 0 and 1, we have x of t equals t minus 1. Between t equals 1 and 2, we have x of t equals the constant a quarter, and between t equals 2 and t equals 3, we have x of t equals 0. So let's go ahead and attempt to solve for a of n for this periodic signal. And it's going to be, according to formula, 1/3 times the integral from t equals 0 to t equals 1 of x of t, which is t minus 1, e to the minus j 2 pi over 3 nt dt. So that gets us from t equals 0 to t equals 1. Then we have to do another integral from t equals 1 to t equals 2. In this case, our function x of t is a quarter, and then again it's e to the minus j 2 pi over 3 nt dt. And then in theory we're supposed to integrate from 2 to 3, but there's nothing to integrate there. So now we have a bunch of cosmically unsavory math to do. I'm not actually going to do it in the video. I'll just show you the answer. But for those of you who want to try to work it out by yourself, the two things that you're going to need to keep in mind are, first of all, over here, you could make this problem a little easier by doing a u substitution. So you could do u equals t minus 1. And then that would leave you with something of the form u e to the ut, or sorry, u e to the au, which you would then look that up in a table of integrals. The integral on the right is pretty easy to solve. That's just a fairly straightforward one. And the other thing I like to do sometimes when I see an equation like this is I like to try to simplify when I can. So for example, you'll reduce the number of things you have to write if you create some sort of temporary variable like alpha. I created one called alpha, and I assigned it the value of 2/3 pi n. And that way, instead of having to keep writing 2/3 pi n, 2/3 pi n, I could just do alpha. So that makes it less chance for screwing things up because there's fewer terms to keep track of. So anyway, I did all that math, and after a lot of belly aching, let's see, why won't this paste? Paste. Let's see, home, paste. Keep source formatting. There we go. We wind up with the following equation for a sub n. And it's not pretty, but it works. And the reason I know it works is I went to Matlab and I typed it in. So let's take a look now in Matlab. Here you have t equals 3, a function to give me omega, a function to give me my a. This is the 2 pi n over 3, and then this is my attempt to incorporate that big gross formula that I just showed you after I did all the calculus. And you can sort of, if you're interested, you can try to solve for it yourself, but if not, that doesn't matter. It's not the point of this. So let's see if this works. I'm going to create a time vector from 0 to 10 seconds, initialize everything to 0, and then we'll loop through 50 harmonics, and then this part here should look pretty straightforward. Just generate a bunch of cosines, and we give it a whirl, and lo and behold, it actually works, which is pretty amazing. So let's go and have a look. I'm going to zoom in, because there is one thing I want to draw your attention to, and that is the fact that although it has basically a perfect shape, you can see that it does not peak where it's supposed to. So this part was supposed to be a constant of value a quarter, and in fact you can see that that's not the value. And the reason for that is that we've neglected to calculate the DC offset. So the DC offset is the a sub 0 term, and a sub 0 term we can get by taking the formula for a sub n, which is 1 over t times the integral for over one period of x of t e to the minus j 2 pi over period nt dt, and you let n equals 0. And when you do that, for any periodic function, a of 0 becomes the average value over one period. Okay, you integrate x over one period and divide by t. So in our case, although our function's a little bit grisly, we can actually calculate the integral over one period by inspection. Okay, the first, if we want to integrate it, first we find this area, which is negative 1/2. Okay, it's negative because it's below the x-axis. Then we calculate this area, which is 1/4. Okay, and then there's nothing to integrate in that third section because it's 0. So the sum of those two together gives me minus 1/4. And then I'm going to divide that by the period, which is 3 seconds, to get a final a sub 0 of negative 1/12. Okay, so that means that I was off by negative 1/12. Let's go try that. And the easiest way to check is, instead of starting with 0, we'll incorporate a constant of 1/12 for our starting point. And now when we run it, you can see that we're right on the money. Okay, now my the DC offset has been handled properly. That's exactly where it should be. This starts exactly at -1, so we're good to go. Alright, so let's, we should probably label this X label time. Okay, so it's a little bit more professional. So, now a word about plotting this. So I've purposely chosen for this example a value of a sub 0 that's negative. And just to remind you, when we go to do our frequency plots, we're going to make one frequency plot that's the magnitude, and we're going to make one frequency plot that's the phase. Okay, and that's because how we always do things with complex numbers. That's supposed to say the angle of A. So just a quick reminder that when you have a negative number, it has a magnitude which is positive. Okay, it has a positive magnitude. There's no such thing as a negative magnitude. The way that you'll count for the minus sign is with the phase. Okay, the phase in this case is going to be 180 degrees or pi radians. And that's how we handle negative numbers. So remember, positive reals have phase of 0. Negative reals have phase of 180 degrees or pi. Positive imaginary have a phase angle of 90 degrees or pi over 2, and negative imaginary numbers have a phase angle of minus 90 degrees or minus pi over 2. So in our case, we would expect to have at 0 a magnitude of 1/12 and a phase angle of either pi or negative pi, depending on how the computer decides to calculate it. It's the same thing. Let's just say pi for the time being. Okay. So let's try that in Matlab and just verify that it works. So we're going to go back to Matlab now, and what I've done down here is essentially try to do just that. Sorry, let me tidy up this plot just a touch. So we're going to take the first 50 harmonics, and I'm going to calculate a sub n for all 50 of those harmonics. And then I know that because of the way I've written my formula, the very first value, the one corresponding to a equals 0, that will get, because there's a divide by 0, that will have the value of not a number. And so I'm going to overwrite the value of AA for which n equals 0. I'm going to overwrite it with negative 1/12. And I'm going to plot my frequencies. And here you go. This is the frequency response. Okay, this is essentially me just plotting. A. Okay, with the only nuance being that I had to do a special case for the n equals 0 term. So here you can see the n equals 0 term with its amplitude of 1/12, right? 1/12 has a value of about 0.08, and that's that right there. And you can see that for the n equals 0 term, the phase angle is pi radians right there. Okay, so that's how we see our DC offset implemented. Okay, so remember, your DC offset can be positive or negative, but it has to have a positive magnitude. If it's a negative number, that just implements itself with respect to the phase.